Thanks for the invitation, and it is my honor to share my latest research with you today. My topic is investigation of rotating store propagation characteristics in a mixed flow pump. My presentation contains 6 sections. Firstly, I will introduce the background. Mixed flow pumps are widely used in agriculture, water conservation, shipping, power, and other industries due to the advantages of high flow rate, high efficiency, and perfect cavitation resistance. But complex instability problems such as secondary flow, rotor-stator interaction, cavitation, rotating store, and so on are unavoidable during the operation of the mixed flow pump. And rotating store commonly happens in the mixed flow pump under pressure load, which will result in unstable flow, energy dissipation, vibration, and other phenomena. In the mixed flow pump, the research on rotating stores started late and the research foundation is weak, but it causes serious instability and cannot be ignored. A number of scholars have investigated rotating stores, such as Zhang found that the performance curve of pump shows the positive slope characteristic under store condition. And according to Miyabi, the rotating store phenomenon is caused by many factors such as tip leakage flow, leading edge voltage, separation flow, and etc. However, the inherent factor causing the rotating store is not fully understood. The mechanism of the energy loss induced by various factors needs to be further explored. Therefore, to capture the main voltage structures in the store flow field and explore the energy loss mechanism under store condition, which has important academic value and engineering application value. The second section I will mainly discusses the research methods. In the current research, we adopt the numerical calculation, and the above table shows the parameters of mixed flow pumps. And as you can see from the pictures, we use the Hexagon mesh for the whole domain of the mixed flow pump. We select the boundary conditions and the turbulence models as shown in this table. We also test the grid independence and the boundary laser Y+ distribution. To verify the reliability of the simulation results, we build a mixed flow pump test bed for experimental research. It is worth mentioning that the velocity distribution of the flow field is obtained through the PRV experiment. The third section studies the energy performance of mixed flow pump. After comparing the experimental and simulation results, we conclude from the results that the head of the mixed flow pump gradually increases with the decrease of the flow rate, and the efficiency is the highest near their designed condition. The head curve presents a positive slope characteristic, which indicates that the rotating store phenomenon occurs in the mixed flow pump. The critical store condition appears at 0.52 of the best designed flow rates, while the deep store condition appears as half of the best designed flow rates. And then we also find that each performance curve has a positive slope. Therefore, the pump will exhibit a phenomenon of rotating store. The efficiency results using the SST-K omega turbulence model are more closer to the experimental values. We also compare the safety results with the PRV. We found that the trend of the streamline distributions by safety and the PRV tests are basically the same. A large backflow vortex is formed at the inlet of the guide vane, making the outflow of the impeller move upward and create a high velocity zone in the end wall area of the runner chamber. The location and the scale vortex in the simulation results are in agreement with the experimental results. In part 4, we will focus on the incipient rotating store characteristics. Firstly, we compare the velocity distribution on the section of the impeller outlet. We use the three turbulence model to show the store vortex in the flow passengers. We found that the three vortex structures in the adjacent flow passengers are captured by the SSTK omega model, which are all located near the outlet of the suction surface of the blades. So the SSTK omega model is most suitable to carry out the parental study. We also compare the pressure distribution of the blade passengers. We found that the SSTK omega model has a good prediction ability for the uneven spatial distribution in the low pressure region and the change of the pressure gradient caused by the initial store. So we analyze the initial store vortex structures use the SSTK omega model. We found that a large vortex at the impeller outlet is captured by the SSTK omega model. The vortex structure stays near the impeller outlet and blocks almost half of the flow passenger. And this blocking makes higher turbulence dissipation and, as a consequence, higher energy loss in the impeller. Furthermore, we found that the vortex flows from the pressure side to the suction side and propagates to the next flow passenger, which leads to an increase in the angle of the attack at the inlet of the blades. Store vortex travels along the direction opposite to the impeller rotation. In the fifth section, we will analyze the propagation characteristics of the store vortex. The first is the propagation characteristics of the store vortex in the impeller. As we can see, each flow channel develops from pre-store stage to complete the store stage in turn, and cycles back and forth. When the flow channels is in the completed store state, the fluid near the wall on the upstream suction surface will be squeezed, and the streamline will deflected, resulting in the downstream flow channels enters in the pre-store stage. After that, the downstream channel enters the store development stage. By monitoring the pressure pulsation characteristics in a single flow channel, it can be seen that the store nuclear manually appears in the area near the leading edge of the blade. We also monitor the pressure pulsation characteristics of different tip clearance. We found that the pressure coefficient is higher for smaller tip clearance, and the clearance in time domain are larger. And the intensity of the pressure coefficient distribution and the propagation characteristics increase firstly and then decrease with the increase in tip clearance. Through a dynamic analysis of the store vortex formation in a single flow channel, it is found that the store vortex core has experienced the process of falling off, developing and collapsing from the leading edge of the impeller. By studying the relationship between the tip leakage flow and the store flow field, it is found that the fundamental reason for the transition from stationary flow state to distorted flow state in downstream flow channel is that the existence of the store vortex in the upstream leads to the change of the flow path. Rain flow distortion is one of the main causes of pre-store and primary tip store. By studying the relationship between the blade tip initial store and the store flow field, it can be found that the pre-store is the trigger signal of the flow passage entering the instability stage and the precursor of the entering the store stage. The initial blade tip store is the trigger signal of the flow passage entering in the store stage, which is the transition process from the unstable stage to the store stage. Section 6 is the conclusion. We can find that the starter area performance curve of mixed pump is accurately predicted by the SSTK omega model. which is close to the experimental results. Under the deep store conditions, nearly 50% of flow passages of the impeller is blocked by the store vortex, and the effective work section is further reduced. The streamline at the leading edge of the store vortex reaches the leading edge of the next blade and overflows, which has the most fatal impact on the head drop of the mixed flow pump. That's all for my report. Thanks for your attention.